Welcome back. This is part 5 of the series on stochastic processes. In the last two lessons, we solved the gambler's ruin problem completely. First, we computed the probability of ruin, and then in the second of the two lessons, we computed the expected length of the game. Both answers came from a random walk that was trapped between two absorbing barriers, basically one player going broke or the other. In this lesson, we set the random walk free. We first classify walks by their state space, walks that are unbounded in both directions, walks that are blocked on one side, and walks that are confined at both ends, like the one we saw before was the gambler's ruin. We look at what a boundary can do to the walk, absorbing it or reflecting it. Then we take the fully unrestricted walk and work out its mean, its variance, and its complete probability distribution after n steps. So whether the walk ever returns to its starting position is a deeper question. That question and a beautiful answer involving generating functions is subject to part 6, our next lesson. So what we did for the gambler's ruin can be generalized. Strip away the gambling story. A walker on the states 0, 1, all the way up to A remains. And that's quite general. Each play is one step right with probability P. I didn't draw it in here, but going this way is probability P. And what's left, probability Q, which is 1 minus P. And then for the two states, 0 and A, as you recall, the probability once you hit these is 1 and going back, and probability 1 and returning back to A. In other words, you don't get out of either one of these. So these are the absorbing states. So gambler's ruin is a finite random walk with both ends absorbing. In this lesson, we classify walks by state space and boundary behavior. So we already have one type here. Then study the unrestricted walk in terms of the mean, variance, and the associated distribution. We have three types of random walks on this slide. The first one is unbounded. So you start at some initial state and then you can move either to the right or left, and there's no bound. So if the probability is higher going in one direction, you may just keep drifting out indefinitely. Then we have bounded on one side, and you have a state here that's either absorbing or reflecting, and I'll explain that in a minute. And you can't go past that on the left, but you can continue going out on the right. The distinction between absorbing and reflecting is absorbing is when you hit this state with probability 1, you come back to it. And reflecting is there's a probability less than 1, greater than 0, that you leave the state. So for example, 0.5. So maybe you come into this state with probability 0.4, and you leave the state with probability 0.5, and you return to that state with probability 0.5 in the next step. That would be a reflecting state. Absorbing is just probability 1 of returning once you hit it. And then we have what we've seen before with a slight wrinkle, because we can have reflecting. In our random walk example, these were absorbing states because it was probability 1 of staying here, but you could have probability less than 1 that you remain, and then the other complement of that probability is leaving again. So you could bounce back and forth between these states if they're reflecting, or you could have one that's absorbing and one that's reflecting. That's also true. But in general, you have unbounded on either side, bounded on one side, and it could be bounded on the right side too. I didn't show that, but that would also come in this category. And then you have finite. And then the one wrinkle or additional feature is these end states here, A and B, or just A in this case, they could either be absorbing or reflecting. This is a bit of a repeat from what I mentioned on the previous slide, but let's just emphasize it. So the absorbing you come into the state with probability P, and then I should have just drawn this down here. You return back to A, and the next step was probability 1, and the step after that was probability 1. So you never leave the state. So that's absorbing, and then reflecting is you have probability Q, whatever that might be, going into the state, and then you leave. I'm showing here 1, but it just needs to be greater than 0. It doesn't have to be 1. In this case here, you are forced to bounce out. You hit here at state 0, and then with probability 1 you leave. But as I gave the verbal example in the last slide, it could be probability 0.5 that you leave and probability 0.5 that you come back to it, and that's also reflecting. And sometimes the terms sticky, retaining, or partially reflecting are used for the case where this probability of leaving is less than 1. Okay, so those are the state classifications. Let's continue. So let's look into the details of the unrestricted walk. Let x sub n be the position of the walk at step n. Each step, w sub n, which this is basically a random variable, is a modified Bernoulli variable with values -1 and 1. Typically, Bernoulli is 0 or 1, but we can make it -1 and 1 just because we want to represent -1 is going left and +1 is going one step in the right direction. Then we can write it down like this. So the position at step n, this random variable, is the initial starting point at x sub 0 plus the sum of the modified Bernoulli variables from the first step up to the nth step. And then I have this statement here, peeling off the last. What I meant by that is you can write this as the sum from 1 to n minus 1 plus w sub n, and then the sum from 1 to n minus 1 of w sub I plus x sub 0 is x sub n minus 1. And so the given that you're in the n minus 1 step, and the Bernoulli variable for the next step, you can determine your x sub n, or represent your x sub n. So this is the Markov property. You only need to know the present state in order to represent the following state. So that was the point to be made here. This is a Markov, this is a process following the Markov property. Then on the right, I have a graph, 4 symmetric walks. That just means the probability of going in the minus direction or the plus direction, in other words, either left or right, is 0.5, it's equal. And these are just simulations. So you can see the darker white line kind of goes down to 0, then it goes up, it goes off a little bit. Same thing for this one here. These other two kind of go down a bit, and then they come closer to 0. So you would expect if you let this run longer and longer that the expected value for x sub n would be 0, and this, in fact, we can show that, but this is just a simulation over 60 steps. The drift of the walk. So we have a probability here, a conditional probability. It's saying the probability that you're in state I minus 1, it's step n minus 1, and you go to state I, it's step n. In other words, you go one step to the right, positive direction, that's P. Then the probability that you're in the same state, n minus 1, or n minus 1 steps, I should say, and you're in state x I plus 1, and then you go down 1 in your next step. So this probability is Q. It's just 1 minus B. So it's just saying that the probability for this particular random walk is P for going to the right, and 1 minus P for going to the left. That's all we're saying here. And in the simulations I showed you, in the symmetric case, P is 1/2 and Q is 1/2. We assume x sub 0 is 0, so at step 0, you're at position 0 on your random walk. That makes the calculations simpler, and it doesn't really, we don't lose anything by doing this. The expected value of just the one of these Bernoulli variables, it's just using the definition for discrete expectation. So it's 1 going to the right, and then -1, the probability going to the left, and we get P minus Q. Expected value is linear, and so we have down here the expected value of x sub n is just the expected value of these Bernoulli variables, and we set x sub 0 equal to 0. So we just have the sum of these, and they all have the same value. So it's just n times P minus Q. This is the expected value. And what I mentioned on the previous slide where we had the symmetric random walk, I said the expected value would be 0. And you can see that's the case here. You have 1/2 minus 1/2, so you would get 0. Now that doesn't mean you're going to exactly hit that every time in a simulation of, in our case, 60 trials. Okay, let's continue. On the previous slide, we computed the expected value for our random walk. And on this slide, I want to compute the variance and the standard deviation, which is just the square root of the variance. So we have the formula here for variance. Let me point to it. So this is the formula for variance of a random variable. In this first part here, it's when you square this, right, it's either 1 or -1. So you're just going to get 1 for the expected value of w sub I squared. So that's 1. Then on the previous slide, we did this computation, and that was P minus Q, and we have to square it. And this reduces to 4PQ. It's a little bit of algebra, which I wrote down here if you're interested. You may want to pause the video just to view this. I took 1 and wrote it as P plus Q, since P plus Q is 1 squared. And then you have the difference of squares, and I wrote that out. And then if you just expand it, you eventually get 4PQ. Now each step is independent, and they have the same Bernoulli distribution. So we can just sum up the variances by Binomial's identity. That's what I'm showing here. So the variance of x sub n is just the sum of these different Bernoulli variances. And so it's just n of these, so it's 4npq. And so this is the variance, and then the standard deviation is the square root of this, so it would be 2 times the square root of npq, which I've shown here. And the drift grows like n, much faster. Drift I'm using, that's just the word for variance. And PQ is the largest at this value here. PQ is the largest when P and Q equal 1/2. So the symmetric walk spreads the most. In other words, it has the largest variation. Well, on this slide, we have an example of a walk bias to the right. We'll take P equal 0.7 and Q equal 0.3. And n steps n equals 100. The expected position would be 40. That's just from our formula. N times P minus Q is 40. Then the standard deviation is the square root of 4 npq, and that's about 9.17. So that's out here at 100 on this graph here. and the graph is 5 simulated paths. We're doing it for p equals 0.7 and q equals 0.3, but we're doing it for all these different number of steps. So basically at 100 different steps. This is the mean here, the expected value, the orange, solid orange. And then if you take this plus or minus 1 standard deviation, that's the amber band. I don't show it here, but if we took 2 standard deviations, we would pretty much enclose all 5 of the simulated paths. And also, as you can see, that it is biased to the right. These are slowly but surely getting further away from 0. Now, if we switched P and Q and made P 0.3 and Q 0.7, then the graph would be going down, the simulations would be going down here basically in the negative area. We can also represent the right and left number of steps. So R sub n counts the number of steps to the right at time n, in other words, after a total of n steps. And similarly, L sub n counts the number of steps to the left. So for example, if we had 7 right and 3 left at n equals 10, then R sub 10 would be 7, and L sub 10 would be 3, and your position at step n would be 4. It's just a matter of taking 3 from 7. And we can represent this more generally with these equations. So your position at time n is the number of right steps minus the number of left steps, as we saw here. And then n is just the total number of right and left steps. That's even more obvious. We can transform this a little bit. We can solve for R sub n here. R sub n equals x sub n plus L sub n. We plug that in here and we get n equals x sub n plus 2L sub n. We can subtract x sub n from n and then divide by 2. And we get this formula for L sub n. And then we can solve for R sub n here. It's just n minus L sub n. And then we plug this in for L sub n. And with a little bit of algebra, we get this here. Okay, so then we have something called parity. The counts R sub n and L sub n are whole numbers. That's obvious. They're just the number of steps. And so n and x sub n are both even or both odd. And that's because of these two equations here. And let's look at one of them. If n is odd and x sub n is even, then an even from the odd number gives you an odd number, and 2 doesn't divide into an odd number, and this contradicts what we just said about L sub n being a whole number. So you need to subtract an even from an even to get another even number, so you can divide by 2. Or if you subtract an odd number from an odd number, again you get an even number, and that allows you to divide by 2. And by similar arguments, you have that here. Okay, so both n and x sub n are either both even or both odd. Okay, so after an even number of steps, n, the walk sits on an even position, x sub n, right? They have to be either both even or both odd. And after an odd number of steps, you're going to be at an odd position, an odd numbered position. So we'll come back to this parity pattern when we talk about first returns to a given state and periodicity. That's in a future lesson, but we'll need to use this again later. We can now compute the distribution for the position of the walker. random walk. So let x be the position after n steps, and that means that 1/2 n plus x steps have been taken to the right, and 1/2 times n minus x steps have been taken to the left. We can check this. If we add these, we get the total number of steps. You notice the x's cancel and you get 1/2 n plus 1/2 n, so you get n, so that's right. Then if you subtract the number of right from, and take the number of left from the number of right, the 1/2 n's cancel and you get 1/2 x plus 1/2 x, because you're subtracting here, and you get x. So that checks out. And we know the probability of going left or right. It's either p or 1 minus p, which we call q. So we just have p to the 1/2 n plus x with the right steps, and q to the 1/2 n minus x for the left steps. But then there's the question of which of those steps was right, and that's just the combinatorial calculation here, and that's this here. So out of n steps, how many different ways can you choose to go right? 1/2 n plus x times. Okay, so this gives you the probability of being in state x, excuse me, after n steps. This distribution here. So if you just plug in different values for x, you'll get the probability after n steps of being in that state. And this is what's known as a binomial distribution. Then the question is, well, when is this 0? So these need to be whole numbers. So if you pick a value for n and x, where 1 is even and 1 is odd, then we know they're not whole numbers in that case, so it won't work. And so that's an invalid position after n steps. And then the other possibility is if x is further than n from the start, then there's no way you're going to get out to state x in n steps. I think that's obvious. So that's probability 0 in that case also. Okay, so let's continue. We're almost done. I have an example on the next slide. On this slide, we have an example of a symmetric walk. P and Q equal 1/2. We start at 0. And we want to know the probability at n steps. We're back at state 0. So it's this probability here. And we have our equation from the previous slide. So it's 100, choose 50. You need to take 50 steps right and 50 steps left in order to come back to 0. And then we just get 0.5 to 100 because these two are equal. And we get about 8%, a little bit less than 8% chance of being in state 0 after n steps. And then I have a caution here. This is just the probability of being in state 0 after n steps. If you ask a different question, what's the probability of the first return to state 0 after a given number of steps? That's a different problem which we haven't solved yet, but we'll get to that eventually. I have some takeaways from this lesson on the right. We classified processes by the state space and the boundaries. And the boundaries are either absorbing or reflecting. And then we had the subcase of partially reflecting, where there was a probability that you might stay in this state, a probability less than 1, and a probability also that you might leave. Then we computed the expected value for the random walk, the infinite in both directions random walk. And that was, we called it drift, but the technical name is expected value. And that's n times p minus q. And then the variance is 4 npq. We calculated that. Then just a few slides back, we calculated the probability and then steps of being in state X, and that was a binomial distribution. And then I mentioned on the last slide that beginning at state 0 is not first returning to 0. So um, we didn't calculate the first return probabilities, basically, that we calculated just the state of being in 0 at step n, but not the first time. That's what I mean by this bullet. We'll get to that actually in the next lesson, which I have mentioned here on the left. So first return probabilities, when does the walk first come home? So when do you first come back to the state as opposed to just being in that state at step n? The law of total probability ties returns to first returns. So we'll look at that as part of this solution. A generating function delivers the answers with Catalan numbers inside. So I'll explain what these are. These are from number theory. Walks in 2 and more dimensions, and Pauli's surprising theorem. So we've been working just in this lesson and the last with one-dimensional walks. Either you're going left or right, but much earlier in these lessons, I talked about the possibility of 2 and higher dimension walks. So you could go left, right, up, and down, and if you go in 3 dimensions, you have yet another way of going another direction. And then, of course, you could even theoretically talk about walks in yet higher dimensions. Okay, so if you like this video, please give it a thumbs up and stay tuned. I should have another 7. That's the plan. I've done 5 so far, and the plan was to have 12 lessons in this series.